Hello, my name is Chrafi. I'm from Morocco. My subject is titled The Effect of Non-Parabolicity on the Transmission Coefficient in ZNO and ZNO doped by magnesium in quantum well and quantum wire heterostructure. My project is realized within the Faculty of Science and Technology in Greenland, University of Sultan Al under the direction of my supervisors, Professor Khalid Rahmani and Professor Azdin Zorqani. During the treatment of my subject, I followed the indicated plan. A small introduction, we will talk about the different type of nanomaterials. After, I will try to explain the method, the finite difference method, to determine the energy in transition of our samples. So we have calculated the electronic state in ZNO Mg ZNO quantum wire structure with 20% of magnesium in both the parabolic and non-parabolic cases. We will see the transmission coefficient of a thin layer of ZNO surrounded by Mg ZNO, and I will end it with a conclusion and perspective. The nanomaterials are materials with nanoscale grain size. So we found the nanomaterials three-dimensional, so it's the bulk, and the nanomaterials two-dimension, and the one dimension and zero dimension, so the nanoparticles or the boxes. Those nanoparticles are field of research and development in several fields, such as in optoelectronic and in medicine. So this nanomaterials has several advantages and is not very expensive and easy to manufacture it. The figure presents a general overview of the effect of the degree of confinement on the electronic structure and on the density of state. The density of electronic state of the wire is in step of staircase. It still represents a quantum of state accessible to the electrons being free in the plane x, y. For the quantum wire, the density of the state always presents a quantum of accessible state because the electron remain free in the x direction. Finally, in the quantum box, the carriers are confined in the three direction. The energy so is totally quantified. The density of state is therefore discrete. Semiconductor materials with a large band gap of system are gaining increasing interest. They are the potential competitor of the other large family of materials with a large band gap. So like the nitride ZNO crystals in the word Z phase, then the presence of the particle effect related to the polarization with internal electric field is more intense than those in the nitride 3-5. So however, ZNO has several advantages. Its substrate is naturally solid, it is of a good crystalline quality, and it is not very expensive and easy to manufacture. So in this work, we are considered the possibility of an application of a good unconstrained quantum wire laser diode. We use the ZNO materials as an active zone in the quantum wire laser. In this work, we consider a system consisting of a heterostructure of ZNO surrounded by ZNO MgO with 20% of magnesium where the growth is in Z direction. So we use the ZNO material as an active zone in the quantum wire. So the transmittance coefficient was then calculated as a function of the magnesium fraction and the width of the active zone and the optimum value of the width of the well. The transmission coefficient is calculated using the finite difference method by considering the parabolic and the non-parabolic modulus of the conduction band. The electronic states in our samples are determined by the approximation of the envelope function. So under the effect of the approximation of the envelope function, the wave functions and the energy levels are obtained by solving the Schrödinger equation, with VR is the crystalline potential and UHRZ is the potential of the heterostructure, where Z determine the barrier and the well interface position. The position taken as the origin of the potential is Z1. The potential of a heterostructure often results from the strip disquantity delta of energy set offset at the interface of the two materials due to the difference in the position of the conduction bands. However, this time the presence of internal electronic fields in each of the two materials will influence it. In this method, we consider a structure as a succession of n plus y layer of delta z thickness in which the mass and the potential are constant. Instead of choosing a mathematical form for the wave function, we assume it's constant in each region. Then we calculate the function x n plus 1 to determine the clean energies. Those clean energies is to find are the confined levels of our layer. So with 20% for magnesium fraction, the evolution of the wave function in the asymmetric cases for the layer Zano unturned by mg Zano quantum while the first result of the value of confined energies. So as below, it's we choose the fundamental level and the first level excited and the second level excited. So the different type of the wave functions is represented the first wave function for the first fundamental level and the second wave function for the first level excited and the third wave function for the second level excited. The conduction band profile as presented present the confined level position and associated envelope functions in Zdano and Mg Zdano with 20% fraction of magnesium. So we choose the width of the well for 6 nanometers and the barriers offsite is come as below, and we found the three confined energy levels E1, E2 and E3. Our result as presented show the evolution of confined levels as function of the width of the quantum while in the parabolic and non-parabolic cases. As shown in the figure below, the non-parabolic band have a very important effect on lowering the position of confined levels. The confined levels are relatively sensitive to variation in the width of the barrier, in particular for the low width of the barrier. The position of the fundamental level and the first excited level located below Vs increase when the barrier is widened. On the contrary, those located in the above of Vs descend in energy. It should be noted that those energies variation are generally low after a certain width of the barrier, considering the value of the barrier 8 nanometers to study the effect of the well width. The following figure is graphically presented the different comfort level evolution in function of the well width. The transmission coefficient of an electron through the potential barrier is written as below. So with the E, the electron energy, V0, the barrier height, and LB, its width, and M, the electron mass. Different variables are involved in the calculation of transmission coefficient: the barrier thickness, the electron energy, or the height of the barrier. We have shown in the following figure the influence of two parameters on the transmission coefficient are the thickness and the height of the potential barrier. Generally, the width of the barrier is the lower the transmission of an electron with a given energy will be. When the thickness of the barrier is 5 nanometer, very few electrons can cross the barrier. When the thickness is less than 5 nanometer, we see that the transmission coefficient is no longer zero for energies lower than the barrier higher. The probability of channeling increase beyond the barrier energy 0.2 electron volt. We observe oscillation related to the phenomenon of quantum reflection on the thickness barrier. That there is a decrease in the transmission coefficient when the magnesium fraction increase. That means that the barrier height increase beyond the barrier energy VB. We also notice variation related to a quantum reflection phenomenon. For the coefficient of transmission, according to the concentration of magnesium, what we choose, that we choose 20% of magnesium, indicated the present the below figure indicated that there is a decrease in the transmission coefficient when the barrier height increase, that the fraction of magnesium increase. In this case, it will be necessary to provide more energy to the electron so that it can be cross the barrier. Beyond the barrier energy, we also notice the variation related to the phenomenon of quantum reflection on the thickness barrier. The transmission coefficient for both parabolic and non-parabolic cases, the both examples present a good optical transmission around 19%. In most cases, thin multilayers have shown different physical properties. The variation of the shape of the individual MgZNO layers has a significant influence on the optical properties and the crystal structure of the MgZNO alloys. It can be seen that the transmission in the case of the parabolic bands are made in a fast way than in the non-parabolic bands. Thus, this result is a good agreement is obtained with the existing literature values. To note, we compare our results with practical results. As you see, these results are very close to each other's. So our result obtained by numerical simulation, and the practical result is by both practical methods, CBR and EGFR. So in this work, we have studied the conduction band profile and theory of calculation of energy levels in quantum while ZNO and MgZNO with 20% of magnesium. So we have calculated the transitions and the energy levels for our cases, the non-parabolic and the parabolic cases. So for the transmission coefficient, it depends strongly on the potential of the barrier and its width. It decreases when the height of the barrier increases and or the barrier is faint. We also note the variation related to a quantum reflection phenomenon. Thank you for your attention.